So Dr. Byrne and Pat will be talking about their experiments with snow. And Jennifer Humphreys, who is a previous master's student of Dr. Chris Byrne, has contributed data to this as well. And she was going to come present and discuss, but unfortunately, she's been traveling from Whitehorse to Inuvik and weather conditions were poor, so she wasn't able to make it on time. So with that being said, I'll just give a quick thought towards how we're going to do questions and such today. Last week, we had a really great question period with Dr. Dumais, where all you participants have to ask questions in the Q&A or in the chat. But we'd like to get the audience more involved. So if you have questions and you're comfortable asking them live, you can send a message in the chat that you'd like to ask a question, and then we can promote you to a panelist and you can ask your question live and have a bit of a discussion. Or if you prefer, you can just ask it in the Q&A and we'll ask for you. But either way, we're looking forward to hearing about your questions. So without further ado, I will stop sharing my screen and invite Dr. Byrne and Pat to give us their talk.
Okay, I'm going to share this screen, which I hope that you can see now.
Yep, sure can.
Yeah, that says you can. And we're going to go on to this. So what Adam has encouraged me to do is to give you some comments about some more applied elements of permafrost science. So what I've decided that I will do is to give you a couple, it could be two, it could be three, depending on how the discussion and the time goes, parts to a series of short descriptions of field experiments that we've conducted using snow manipulations. So all of these are to do with permafrost. The first one is from the continuous permafrost zone from the western Arctic coast. The second one is from the northern or the widespread discontinuous zone in the central and northern Yukon Territory. And the third one is, if we get there, is from the limits of permafrost in the southern area near Whitehorse. So that's more in like the sporadic permafrost zone. So there are three different types of activities. And in each case, what we've been doing is manipulating the snow to see if we can have a geomorphological result. In these cases, two of the cases, the ones that Jen and Pat will discuss, or I will discuss on Jen's behalf and Pat will discuss, are associated with the transportation infrastructure as well. So we'll begin with the first one, and this is an activity that was started in 1998 at the Ilisarvik experimental drained lake site. Now, Ilisarvik is a lake on the north coast of Richards Island in the western Arctic coast of Canada. It was drained in 1978 by Dr. Mackay. And he did that in order to have a full-scale field experiment on permafrost aggradation. This particular topic is one that has been written up a lot in the literature, but what I'm going to talk about is how after some time we tried to restart ice wedge cracking at the site. Now, as many of you know, ice wedges are very common in sedimentary environments in the continuous permafrost zone. What I'm particularly interested in this presentation are these thermal contraction cracks, which occur are the reason for the genesis of the ice wedges. I should say to you all that one of the things that last week we learned, which has caused considerable reflection on my part regarding contraction cracks, was that we heard on Monday last week that Dr. Arthur Larkenbroek, who wrote the standard theoretical treatment of ice wedge or thermal contraction cracking, he passed away on Monday at age 95. And so in some ways, the motivation for this is to think a little bit about how he thought of what was going on in the ground as the temperature in the ground was reduced in the wintertime. So I really want to mention two people whose thoughts have been influential in the way that I think about ice. One is Dr. Larkenbroek, and the other, of course, is Dr. Mackay. We're not going to look at the ice wedges themselves, but rather at the cracks in this presentation. So what you can see here is a map of the Mackenzie Delta area in the Western Arctic of Canada. Inuvik is the place where most people arrive. Now, of course, you know there's a road from Inuvik to Tuk, and that road crosses tree line. But an area which is not connected by road, but is connected by snow machine in the wintertime and by helicopter in the summer, is the site Ilosavik, which is the location where there's the drained lake that Dr. Mackay, as I say, drained in 1978. It would be very difficult today to drain a lake. The amount of permission that you would need today to do that would be astonishing. But he had to go through all the regulatory hoops, and he got all the different permissions. And when the lake drained, and the lake drained in about 8 hours from when he started it at 8 a.m. in the morning on the 13th of August, 1978, until about 4 p.m. It was essentially drained by 4 p.m. So it was a catastrophic drainage. And you'll notice that this is the channel that drainage cut as the water was taken out. And essentially, he made the water, he incised the ground by thawing ice wedges with a water pump that thawed out the top of the ice wedge. And then as the ice wedge got below the level of the water in the lake, then the water from the lake just gushed out into the ocean. This picture is taken in 1980, which is 2 years after drainage. You can see there's still relatively little vegetation in the lake. And over those first 2 years, there were 4 ice wedges that developed or ice wedge cracks that developed within the lake basin. We're going to spend most of our time thinking about the area that is near crack number 3. In this location, the ice wedge was developed from 1980 through till 1989. And over those 9 winters, a crack was regularly observed in the lake bottom, something like 70 meters long. You notice here is an image that I think I took in 1986. And there's the crack. And then you can see the crack has penetrated up through the snow cover. You'll notice that the snow at depth is very dirty because lots of Ilosavik was bare at the time. Because it was bare, there was relatively little snow depth. And then subsequently, as the surface has been covered by snow, the further snow that's been blown around is quite clean. But this material is the initial snow cover from that winter. And there you can see the crack. This trowel is 22 centimeters long. So that gives you an idea of the scale. And these ice wedge cracks appeared every year for about 8 years or 8 or 9 years. After 1989, the ice wedge stopped cracking. And in 1999, we dug up the ice wedge. And when we dug up the ice wedge, we could see that what had formed was about 22 centimeters across, which is roughly the length of the trowel. And you'll notice the foliation in the ice at that's in this exposure. Now that reflection there, that is the reflection from the flashlight. This isn't that there's fire in the ice. There's maybe some people who have imagination of that nature, but this is just a reflection of the flashlight. But you'll notice the foliation. And as I say, there's cracking of about 9 years that led to a 22 centimeter ice wedge developing at that point. But after 1989, there was sufficient vegetation that had grown on the surface of Ilosavik that meant that the ice wedge stopped cracking. And so from 1989 onwards, this site became quiescent. You notice that there is a little trough that sits above the ice wedge. So the ice wedge itself, as it developed, trough developed, and these little hoop crack meters are crack meters that Dr. Mackay devised and which he used to determine the growth of the ice wedge each year. And these are positioned within the active layer. And indeed, the separation of each side of these hoop crack ridges was something that he measured on a regular basis during his 3 to 4 visits to Ilisarvik each year. But he also noticed that during the summertime, then the hoops came together, because in the summertime there's expansion of the ground just as there's contraction in the wintertime. And so the ice wedge above and the active layer above the ice wedge contracts. And as a result, he documented oscillations of the ground above the active ice wedge. Now, when this was, as this vegetation grew on the surface of Ilisarvik, then the snow depth also increased on the surface of Ilisarvik. And as the snow depth increased, the temperature in the ground similarly increased. I'd like you to notice here that this picture is taken in 1990, and you'll notice the grasses and sedges, which are about 40 centimeters high. And then in the very back of the picture, there's 1 or 2 little bushes that have grown up. So in general, this is an area where there's a very good view. There's nothing obscuring the view. So the amount of vegetation is not very great, but sufficient. It's sufficient that a snow cover of something like 40 centimeters accumulates on the ground surface. And a 40 centimeter snow cover is sufficient to retard the evacuation of heat from the ground in the wintertime. The next picture that you will see is it shows the temperature envelope for sites in the hills around Ilisarvik, that is the undisturbed permafrost, and sites within the lake basin itself. And you'll notice in these 2 temperature envelopes that the undisturbed tundra has a temperature that is between -6 and -7. Now, when Dr. Mackay drained Ilisarvik, the temperature in that environment was about -8. So it's warmed up due to climate change by a degree or so since then, and more in the last 20 years. But you'll notice that in this case, we have what you would think of as a relatively standard temperature envelope. It has a large amplitude at the surface, and by the time the measurements are made at 11 meters or so below the surface, then the amplitude is considerably reduced. On the other hand, when we look in the lake and the lake basin, don't forget, when the lake was drained, the lake basin had no vegetation, so there was no snow, and so the ground got very cold, and permafrost was established right from the beginning of the lake basin. But you'll notice here that there's very little separation between the maximum and minimum curves of the temperature envelope. And this is because the ground is still freezing at depth. So even though the temperature is below 0, because there is salt in the groundwater, and because and as a result, the freezing point of the groundwater is depressed, then the variation between the maximum and the minimum at depth is very, very small. So there's hardly any fluctuation in temperature. You'll notice also that the temperature is in general above -1. So that indicates the temperature of freezing. But you'll also notice that there is a temperature gradient in this in the undisturbed temperature in the near surface. Essentially, we have an equilibrium environment where there's hardly any change in the mean annual temperature with depth. But in this case, there's a very clear change in mean annual temperature with depth, such that within the lake bed, the temperature is rising with depth. And at some point, and we think it's something like 20 meters below the surface, the ground is then at 0. And then the bottom of permafrost, the bottom of the Talik at Ilisarvik is something like 33 meters below the surface. So there's a small area, maybe 5 to 10 meters thick, which is still unfrozen. The important point is that this area is very warm. So beneath Ilisarvik, even though at the very beginning it was cold enough for ice wedge cracking to take place at the top, it's still very warm at depth. So what we decided to do was to see if it was possible to reinitiate ice wedge cracking at the site number 3 that you saw on the first slide. And so what we have here is an experiment, a field experiment, where we take the vegetation around the ice wedge. There's one of those hoop crack meters. So the ice wedge, which we'll see on the next picture, the ice wedge trough runs about here. And we cut the grass at the end of August. Now the grass was about, or the sedges were about 40 centimeters high, and the grass is cut at the end of the summer so it doesn't grow again. And the result is that we establish within Ilisarvik Basin an area where the snow accumulation due to trapping by the vegetation no longer takes place. We began the grass cutting in August 2020. So this is a view from the air of the long ice wedge at Ilisarvik, and you can see the area has been cut clear. And then on the other side are the areas where the vegetation has been left undisturbed. So there's a substantial amount of vegetation here where the snow depth will increase. And then in this area, we anticipated, and indeed it was the case, that the snow depth should be substantially reduced. And the next image is a picture of what it like in the winter time when you, sorry, the next image is of the whole lake basin itself. And the whole lake basin itself shows you the cleared area. And you'll notice this is about 50 by 75 meters. And then surrounding it is all the slowly recovering or the slowly succeeding vegetation. So this is about what, 35 years after the drainage of the lake. You'll see there still are some bare areas in the lake, but there are now bushes and shrubs that have grown up substantially. So now we're going to look at the snow cover, I think, in this portion of the lake. So there's the snow cover next to the ice wedge. You can see all the material along here that's associated with the ice wedge. And there's somebody standing in the far back. I don't know if anybody of you recognize this person, but he works now for the Geological Survey of Canada, and his name is Peter Morse. And you'll notice, if you know Peter Morse, he's not terribly big, but he has very big boots on here, and you can see the snow depth is not very great, something like 10, 15 centimeters in the cut area, whereas in the uncut area, the snow depth is quite substantial. So the first thing that the first data that I'm going to show you is the difference that arose in the amount of snow that was on the surface. The densities of the snow didn't change very much, but the depth of the snow changed substantially. The first 2 years of monitoring, we didn't do anything. We just tried to measure the ground temperatures before they were disturbed. And subsequently, there was disturbance. So from the winter of 2000 and onwards, we have a change in the snow depth between the uncut area and the cut area. You notice from the data at the bottom of the slide that before the cutting, the snow depth at the site was about 45 centimeters. And after the cutting, the snow depth is about 18 centimeters. So there's a reduction of over a half in the thickness of the snow cover. Now, one of the most interesting elements of this is that when we don't actually, by cutting, we don't affect the summer temperature very much. And that's because this vegetation grows in the summer, and then it's only cut towards the end of the summer. So the summer temperatures stay the same. It's the winter temperatures that change the greatest. So it's interesting to notice the change in the active layer depth. And that is that before the cutting took place, we had an active layer that was something like 80 centimeters deep in that region. But after the cutting took place, the active layer thickness was about 60 centimeters. So there's a change in active layer thickness, but it's not related to change in summer temperatures. It's as a result of changing winter conditions. So one of the elements that is important to pick up is that the thermal regime of the active layer, which we usually think is associated with summer conditions, is also substantially affected by the winter conditions. You'll notice here, before we look at the data at the bottom of the screen, you'll see that before the cutting, it was about, on average, 85 centimeters thick. And the decrease was about 20 centimeters over that period. Now, in addition to measuring the active layer, the other thing that we did was to measure soil temperatures in the cleared area. And the soil temperatures were measured at 3 points, 25, 75, and 125 centimeters depth. You'll notice that the 25 and 75 were within the active layer before the clearing took place, and the 125 was at near the top of permafrost before the clearing, and always remained in permafrost subsequently, and 75 became part of permafrost. So at the end of this little section, we're going to concentrate on what's happening to the soil temperatures. So here we have the soil temperatures on the left-hand side before the cutting took place. You'll notice that the minimum temperature is about -4 Celsius, and within the permafrost, the minimum temperature doesn't even drop below -3 Celsius. So it's about -2, the minimum temperature. You'll notice also that there's a long period of what we call zero curtain, which is when the top of permafrost or the active layer is very close to being isothermal. And so we have a temperature of 0 at the very top of permafrost for about 3 months or 4 months over the different periods on this slide. So there's a significantly long period during which the top of permafrost stays at close to 0. After the cutting, that period declined substantially. So it went down from 3 months to closer to 2 months. And so that's one of the main impacts, is that the change of the snow cover also means that the top of permafrost cools down substantially. Now, I'd like to show you one picture, which I'm going to show you twice. And this is a diagram which indicates the temperatures at 25 centimeters and at 125 centimeters. I think that's right. Over a 10-year period, 11-year period from 1998 to 2009. This first line indicates when the cutting took place, and this second line when the cracking began. You notice that before the cutting took place, the ground temperatures were very high, as I indicated before. Permafrost still existed in the site, but the mean temperature of the permafrost was about -1 or so. So the mean temperature we have in Ilisarvik, we have a very high mean temperature. The reason for this is the snow cover on the surface is restricting the evacuation of that heat, which is down there in the warm talik beneath the surface. So that the slide I showed you beforehand of the warm ground temperatures below Ilisarvik, that heat is unable to leave because of the snow cover on the surface. Then we cut the grass and we reduce the snow cover. And that's really a step change. So there's a very sudden adjustment in the snow cover, but the ground temperature doesn't cool off to a level that would facilitate ground cracking immediately. It took about 4 seasons for that to take place. You'll notice here the ground temperature at the top of permafrost is declining over time. So from about -1 down to about -5, -5.5. At the surface of the ground, the temperature is declining from, again, about -1 down to about -6. So you'll notice that at this point, we have a reversed thermal offset. So the thermal offset is normally higher or the ground temperature is normally higher at the ground surface than it is at the top of permafrost. And the difference between those two we call the thermal offset. But in the case where the ground is cooling, which is what we induced by cutting the vegetation and reducing the snow, then the thermal offset flips around in the other direction, and the surface is actually cooler than conditions at depth. It will take some further time for this to equilibrate again and for the ground temperature to become lower than the surface temperature. Now, it's unlikely for that to happen very quickly at Ilisarvik because of the amount of heat that is coming from the talik that is below. So it cooled off for 4 years, and then after 4 years, we had a crack that appeared in the ground. The first 4 years of cutting, there was no cracking. So it's not as if we can just simply adjust the surface and instantly things happen at depth. It takes time for ground temperatures to change and it takes time for the effects of that to be noticed within the ground. So we'll go back to this slide again, and you'll notice here that after the cracking had taken place, there were some very cold or very low temperatures that were measured near the surface. But you'll also notice that there were cooler conditions in the ground before the cracking took place than after the cracking took place. So here was the first year of cracking, and this is the second year of cracking, but these years are warmer than the conditions that occurred before the cracking took place. What this tells us is that the ground is tuned up, or the ground becomes accustomed to cracking. There are things that take place within the ground that are taking place deeper than the area that we can measure, which facilitate the continuation of cracking. And so what we've measured in the top 125 centimeters is probably insufficient to entirely describe the cracking regime within the soil. And so what I'd like to the way I'd like to summarize this portion of our webinar is, first of all, to notice that the system takes some time to respond. It took, in this case, about 4 years to respond to the step change in surface temperature. Secondly, we had an unexpected adjustment in the active layer thickness. The active layer, in this case, was being controlled by the winter conditions, not by the summer conditions. Thirdly, the thermal offset flipped over so that the near surface temperatures were lower than the temperatures at depth on an annual basis. The fourth one is that the critical thermal conditions, those things that facilitated the cracking, may indeed have been associated with areas deeper in the ground than the top of permafrost. And finally, I'd like to point out that the cracking, once it started, it continued. And that means that there was some dependence on antecedent conditions that took place that after the cracking had started, that enabled it to continue, which were different from the conditions that occurred before the cracking had begun in the first place. So that's the end of this little section. And I have acknowledgements here for Dr. Mackay, who drained the lake, Dougie Essagok, who has been a great assistant and field companion for many of us who work in the Western Arctic, and then the 3 agencies who sponsored the main part of this research. So I'm going to stop sharing that. And at this point, I'm going to invite questions, Adam, if you would like.
Sure. So if there's anybody in the audience who'd like to ask a question and maybe wants to ask one live, you can put your hand up and we'll bring you on as a panelist, or you can type it in the Q&A. We do have 2 in the chat so far. The first one is they were wondering if you were, like after you clipped the grass at the site, if you removed the clippings, or were the clippings still there, and would that impact the insulation of the ground?
They blew away. It's
Okay.
next to the ocean, and so there's quite a lot of wind. That's one of the reasons it's an enjoyable place to work, because there's very few mosquitoes because of the wind. And so the grass, it was on the ground for a day or 2. It became dry, and then in the first time we had any wind, it would blow off. At the end of the summer, or at the end of the period, within the trough itself, there was maybe an accumulation of grass. And so what we would do is to clear out the trough. And then that grass again would blow away. But that was how we got rid of it, rather than just leaving it on the ground itself.
Cool, thank you. I believe it was Brandon who asked that question. If you have any follow-ups, you can feel free to pop it in the chat or raise your hand. But we have another question from Marianne, and she was asking, she said you missed the beginning of the presentation, but she was wondering about the evolution of snowfall since the beginning of this experiment. Had it changed at all? Was that considered in any of the results anywhere?
The evolution of snowfall is an interesting point. And it's interesting because this location is right next to the ocean. And because it's right next to the ocean, there's a lot of snow that is blown in horizontally. So the amount of snow in the Western Arctic is quite low. Over the year, the snowfall the Tuck average is about 130 millimeters of snow. That's for the year, for the whole winter. But at this location, we get much more snow than that. And that's because when there is a strong wind, and the strongest winds blow from the northwest, come from the ocean onto the land, they bring lots of snow with them. And that snow gets stuck in the vegetation at Ilisarvik. Now, at the very beginning, when there was no vegetation, and you saw that there was some dirty snow because there were bare areas that would have soil picked up and then deposited later, further downwind in the snowpack. But after, in the period as the years have gone by and as the vegetation has grown up, then the accumulation of snow in the basin is largely associated with the incidence of winter storms. And the winter storms begin in October, but in October, it's often quite wet precipitation, so they don't blow, it doesn't blow around very much. But by the end of November, there's a substantial amount of snow blowing around. And that's the stuff that gets caught in the lake basin. We haven't published this yet, but we alluded to it in Alice Wilson's master's thesis and in her conference paper. But there are areas at the edges of the lake basin now, where the vegetation is sufficient that the snow depth is over a meter. And that's, again, not snow that has fallen from the sky, but snow that has blown in from the side.
Interesting. Thank you. So we have someone who's raised their hand, Thomas. I'm going to promote them to a panelist so that they can ask the question. And hopefully they didn't accidentally raise their hand and are suddenly going to be a panelist for everyone to see.
Oh, he's there. He's coming.
So Thomas, you can go ahead and ask the question.
Well, thanks. I was just wondering, you very quickly talked about salinity. Did you somehow map how salinity evolved over the years from the lake was drained? Did it percolate further down? What happened? How did that affect temperature and frozen conditions? And what is frozen and unfrozen?
So you may, Thomas, have seen in some of the pictures that there is a pond in the middle of the lake.
Yes.
And the pond is about 4 meters deep. And so the pond does not freeze to the bottom. In the wintertime, water is expelled from the aggradation of permafrost in the Talik into the pond. And so it's possible to have some idea of what's happening to the salinity. I don't, in my head right now, have the salinity values, but we have not only drilled into the Talik and obtained Talik water that has come up under pressure, but we've also looked at the salinity in the pond in the wintertime. In the wintertime, the pond surface domes up about 1 meter high because of the water that is being squeezed out as with permafrost aggradation, because the sediments are mostly sand. So that's what we can tell you about salinity. But if the water, the groundwater was not saline, it would not be still moving at a temperature below 0. And so there are areas where we can puncture the surface sediment, and to about 4 meters, the depth, the ground is ice bonded. Below 4 meters depth, the soil is still got some ice in it, but the drill will penetrate very quickly. And below 8 meters, the material is unfrozen. But as you saw from the temperature profile, the temperature is below 0. And what I have not done is to examine those temperature profiles at depth with time, although we have those temperature profiles. And so I can't comment on the evolution of salinity at this point, but it is an interesting question. But we do believe that the reason for the persistence of the Talik is associated with the continuing freezing point depression of the water as as the ground above it freezes.
Yeah, thanks. Yeah, I was very interested in the evolution part. I thought that was, yeah, very interesting in relation to what I did work with.
Good.
Awesome. So we have one other question in the Q&A, but I think I might save it until after Pat's talk. So I'll read the question and then you can decide if you want to answer it after the next presentation, because I believe it's about roads. So Terry Brooks says, I'm interested in the changes in the road bed temperatures with the construction of a road in virgin areas. Is there a rule of thumb for time of long-term equilibrium for temperature/depth for the active layer? So is that something that you kind of start to cover in the next presentation, or do you want to answer that now?
I don't believe there is a rule of thumb for the duration of disturbance. The simplest approach that I think we would make to something like that is to take a Stefan solution approach. And because almost all disturbances, the rate of change of the rate of disturbance declines with time as the disturbance penetrates further into the ground. So I think part of the answer to your question is how far in the ground are you, what is the depth in the ground that you're concerned with? Because if it's near the surface of the ground, then the disturbance occurs quite rapidly. But if it's at a depth of, let's say, 10 meters below the surface, then the disturbance will take a substantial amount of time. And so the time frame is dependent upon depth. Of course, the total disturbance is also dependent upon the magnitude of the disturbance at the surface. We are going to, in the next section, talk a little bit about temperatures under artificial disturbances. But that would be what I would suggest would be the most rapid answer to that question. Good question, though.
Awesome. Well, thank you so much. So I guess we'll move on to the next presentation. And same as before, if you have any questions during the presentation, just feel free to pop it into the Q&A.
Okay, so our next presentation concerns a series of field experiments that were conducted along the Dempster Highway in the Yukon. Both of them are associated with highway. And the first experiment was the master's thesis of Jennifer Humphreys. As I say, I'm sorry that she's unable to be with us today, but she's actually traveling through exactly the part of the road we're going to be talking about today, possibly as we speak. And then the second section, I'll hand over to Pat, who has just completed a winter of field work in the southern Dempster Highway. So in the first case, Jennifer was working with snow fences at the north end. Sorry, I'm going to pop this up here. She was working with snow fences at the north end of the Dempster Highway. This is very close to the Yukon NWT border. It's this little red area that's on the first of these of this map, and the area is right close to the border. And this line indicates the Dempster Highway. And along this section of the highway, there are very, very strong winds that blow from time to time in the winter, and they blow from the east across the highway. This image I'm pointing out now is looking southwards. So east is on the left and west is on the right. And the winds blow from the east down this gradient across the highway. This is a Google Earth image of the terrain in the region. You can see there's a ridge here on the east side of the highway. And essentially what happens is that the other side of the ridge fills up with cold air from time to time in the winter under inversion conditions. And when this basin has filled up, some of the air spills over onto the top of this ridge and then accelerates downhill because it's cold air and therefore heavy, high density air, accelerates down the hill and crosses the highway. Now, the velocity of the wind when it gets to the highway can be approaching or upwards of 100 kilometers per hour. So these are very strong winds and they blow lots of snow across the highway. And of course, there are two problems. The first is that vehicles that are returning from Inuvik empty, which have a very large surface area. This would be 18-wheeler trucks. They are driving perpendicular to the high wind, and from time to time, these things are blown off the road. There is actually on YouTube a video of somebody with a dash cam, and he goes over the embankment. He's blown over the embankment and into the ditch. And you can listen to what he says when that comes down, or if you wish, you can block your ears because the language is not very clean. Anyway, the other element is there's a lot of snow that is blown across the highway, and so it becomes a hazard for driving. So what the Highways Department was interested in doing was determining whether some snow fences that could be placed on the east side of the highway would actually manage the drifting of the snow. And our concern was that in the long term, the snow fences might become unsustainable if the permafrost beneath the snow fence was thawed out. So the next slide is an indication of this area. And you see here we have a snow fence that was erected in the fall. There's the road on the side here, and there is a little drift that has accumulated in the first 6 weeks or so of the winter time. There were 2 locations on the highway at kilometer 452 and 456, and at 452 there were 3 snow fences placed in sequence. At 452 there were just 2 snow fences placed in sequence, and these snow fences filled up with snow as we will see, in the first part of the winter. This is an indication of the wind speed which is observed, and this is the winter wind speeds. That's between December, January, February, which is when the strongest winds are observed. You'll see here in the summertime, in the spring, and in the autumn, there are other winds, but they're not nearly as strong as except for a short time in the autumn. They're not nearly as strong as the ones that are observed in the winter time. There is a paper in the last Canadian Permafrost Conference proceedings which describes the wind regime in Hurricane Alley, which Jennifer published. This area is known by the maintenance staff as Hurricane Alley. So here's an indication of what happened with the snow at within the 2 sites. There's one location, kilometer 452, where you can see the snow accumulated substantially over the winter time. But at that location, between December and March, there's relatively little change in snow depth at the snow fences, and some change in the undisturbed environment. And similarly at 456, where there are 3 snow fences, you'll notice that they basically had filled up by December. Now, the density of the undisturbed snow is between 0.2 and 0.3, and the density of the snow in the snow fences is about 0.4 to 0.5. And the reason for this is that in both environments, there is the wind blasts the snow the snow is pummeled against the snow that's accumulating on the ground, and the material, much of the snow, of course, blows away. But there is snow that remains behind the snow fences, and they have a very high density accumulation. Now, this is the thermal regime between the snow fence area and the natural tundra. And you'll notice immediately at kilometer 452, and again at kilometer 456, and it's most well defined at 452, you'll notice that the impact of the accumulation of snow at the snow fence is most evident at the beginning of the winter. So in November and December, the ground temperature is still remains close to 0. In other words, the freeze back is still continuing within the active layer, even though in the natural tundra it's already frozen, and that's because of the accumulation of snow. It will not be a surprise to you that the snow accumulation retards the freezing, and as it retards the freezing, it raises the ground temperatures. So in both locations, we have the same thing. A little bit more variation at the 3 snow fence location, and that's because at the 3 snow fences downwind, the the accumulation was less than it was upwind. And so there is some variety in the response of the treated areas in terms of ground temperature over the winter than it was in the untreated areas. But you can see clearly that there's an impact on ground temperatures. And if we summarize those, then over the course of a year, at kilometer 42, where there were the two where there are two snow fences, then in general it's actually slightly warmer than the other site. But at both of them, the impact of the snow fence is almost exactly the same on annual temperature. So the temperature at the top of permafrost, due to that snow fence, erection of the snow fence, increases by about 1 degree. Now you'll notice that the temperature at the top of the ground, that's at 10 centimeter depth, that increases by a larger amount, not very much more, but by about half a degree more. You notice also that at both of these sites, the temperature at the bottom of the the temperature at the top of permafrost is lower than the temperature near the surface. This is the thermal offset that we would anticipate. But you'll also notice that this disturbance actually increases the thermal offset. So in this case, the thermal offset is steeper after the disturbance has taken place than it is before the disturbance. And so really all I want to point out from this particular field experiment is that the snow fences were effective in terms of their ability to retain the snow. The thermal effects were amplified in the early winter, more and the greater early winter effect than late winter. The density of the snow, which was so high, in part reduced the thermal impact. We would have thought that with a substantial snow cover, the thermal impact would be much greater than 1 degree. The change in temperature is much less than we would, the warming due to the snow cover is much less than we would have anticipated because of the high density of the snow. And then finally, I guess what we're reassured by is that the snow fences at this point are not doing anything to suggest that the permafrost at the site is likely to degrade. So they are a long-term position. I think if they were to be operating and if being effective year-round, then or all winter, then you need to have more snow fences or larger snow fences. I don't think we would want actually to have larger snowdrifts. I think it's better to have more little snowdrifts than a few big snowdrifts. And so the benefit to the maintenance people, it came from the fact that they didn't have to clear the road near the snowdrifts up until December, but after that the fences effectively had filled up. So that was Jennifer's item, and now I'm going to hand over to Pat Jardine, and he has just completed his field work and is beginning now to write up his work on another experiment with snow that took place at the southern end of the Dempster Highway. Pat?
All right. Hi, everyone. Yeah, like Chris mentioned, I'm his master's student. I spent this winter up in the Yukon doing field experiments that were testing snowpack compaction as a method of reducing ground temperatures alongside linear infrastructure, so roads up north. If you go to the next slide, Chris. Now, this is my main field site. This is around a kilometer 96 of the Dempster Highway. After doing some location scouting, I found this really long, straight section of road that was perfect for testing because it allowed me to divide it up into separate sections where I could treat differently with different levels of compaction. But before I get into that in more detail, I wanted to go over some background information as to why I was doing this experiment. To start with, there was a team led by Emma Stockton that measured ground temperatures approximately 25 kilometers north of this field location, underneath the road embankment, the highway center line, and the field beside the road, which is mostly left undisturbed. Now, what they found were that ground temperatures were fairly low, approximately 2 degrees on average below the highway center line and in the undisturbed tundra alongside the road, but they were significantly higher at about 0 degrees underneath the embankment toe. Now, the reason for this is mostly due to the large snowbanks that gather up alongside the embankment that you can see a good example of in this picture. Snow is a very weak insulator, so it acts as a blanket and it blocks heat from flowing out of the ground. And the idea for my experiment is to compact the snow, mostly by getting the air out of it. This will cause it to become a much better thermal insulator, and it'll allow the heat to flow out of the ground more easily. Now, this idea wasn't just originated for my experiment. This was tested this was simulated in a 2017 paper written by O'Neill and Byrne, and the results were very encouraging, but my experiment is the first time that it was actually tested in the field. So what I did was divide this approximately 600-meter section up into 10 different test plots, each 50 meters by 5 meters, and I compacted the first plot once every month through the winter. The second left undisturbed. Third, I compacted every second month. Fourth, undisturbed. Fifth, only once in the middle of the winter. Sixth, undisturbed. Seventh, I compacted the first, second, and third month. Eighth, undisturbed. And ninth, I compacted the third, fourth, and fifth month. And the final plot I left undisturbed as well. Now, if we go on to the next slide here, this is the method that I chose to compact the sites. I was working with operators from the First Nation of Natchanaakton. First of all, you can see we're no longer at the Dempster sites here. I also had several field sites surrounding their hometown of Mayo, so I could see how compaction was affected by operating in a variety of conditions. But I used the exact same compaction technique and plot dimensions for all of my sites. The contractors were Natchanaakton land guardians, which means that their normal job is to patrol their very large territory and checking mostly for illegal hunting and logging and things like that. And that meant they're extremely comfortable on their snow machines. So I instructed them to drive back and forth over the 50-meter compacted sections repeatedly until further runs no longer made any visible difference in snow depth. And they're able to do this very quickly in about 10 minutes per site. And yeah, like I said, the test section layout was the exact same in Mayo and the Dempster, where there was a compacted section and a control section, both beside each other, and I was aiming to compare the two of them. If we could go to the next slide. Here you can see the aftermath of what the compaction looked like. We're back to the Dempster, of course. These plots are directly adjacent to each other, and I'd like to draw your attention to the road, if you can see it here under the speaker pictures. The road is not visible in the control section because the snow is piled up right alongside it in its natural state. Whereas in the compacted section, you can see after the Natchanaakton workers were done, you can see the embankment road just under the snow, starting to change the dimensions there. So it just is proof that the snow depth did change significantly, even though it was a little tough to tell at times when I was actually in the field. So if we go to the next section, I can show evidence of that. Here is the control section, which was on the far south end of the plot. Was not disturbed whatsoever. And the solid red line underneath it is the compacted section, which was compacted once every single month. So you can see that the difference between these sections was small to start off with, but beyond that was typically about 20 centimeters. And alongside this data, I also have data about the snow density. So that found that the compacted section, along with having less snow, it was more dense, which has high implications for the heat flow. And this was about what I would expect going into the experiment, that it would cause a significant difference in snow depth. But I was a bit worried that the snowmobiles wouldn't be heavy enough to cause a significant change, but it seems as though that wasn't an issue based on the results. Go to the next slide. Now here is the difference in temperature that this treatment caused throughout the winter. This was measured by a thermistor, which was put inside a metal case at the beginning of the winter to protect it and placed at the bottom of the snowpack. I was not able to get to my sites early enough to place these canisters before the snowfall, so I had to sort of dig out a hole and place them right in the middle and then fill it up again, which is not perfect since there might be slight variations in their depth, but it's enough to give a general sense of what's going on. You can see early on through the winter, the temperatures are fairly close, but right away, the monthly compaction site had a temperature that was significantly lower, especially during cold periods. It seemed to react more quickly to that change. And then in approximately February, it started getting far colder in the Yukon sites. And that's when the monthly compaction really started to cut away from the control sites and start to get a significant temperature decrease. You can see it peaks at around maybe 10, just less than 10 degrees at one point, difference between them in February, but for the most part, the difference is about 5 degrees. And while the change was largest in the sites that was compacted every month, we found similar results for every one of my test sites. And we can see that in the next slide. So here is the average temperature throughout the freezing season for each of the 5 Dempster plots. At the monthly sites, the control plot had an average temperature of 5.7, whereas the compacted plot had 8.8. So that was a difference of 3.1 degrees, which was the largest, along with the difference in the early winter compaction. So just to go over these again really quickly, monthly compaction was compacted every single month. Bi-monthly compaction was compacted on the 1st, the 3rd, and the 5th month. Midwinter was compacted only a single time in the middle of the winter. Early winter was compacted in the 1st, 2nd, and 3rd month, and late winter was compacted in the 3rd, 4th, and 5th month. So I found it interesting that compacting in only the early winter actually caused just as much cooling as compacting every single month. I think that really emphasizes how important it is to get on this right away and start compacting for the beginning of the freezing season when atmospheric temperatures are at their coldest, and to initiate the freeze up process as quickly as I could. And another thing that I found interesting here was that just compacting a single time in the winter, which was maybe 10 minutes of work, was enough to reduce the freezing season average by 1 degree, which was the lowest of these results. But considering how little work that was, I thought that was really interesting. And we'll see that undisturbed tundra was measured about 20 kilometers north of this site, and it was negative 11.4 degrees. So here you can see the warming that the snowpack is causing at all of the sites, including the compacted sites. But it seems as though the compaction process was enough to reduce that disparity just a little bit, and that could potentially have big implications for ground maintenance if we're able to reduce this problem moving forward. And next slide, please. And I wanted to acknowledge the help of Jen Humphrey and Emily Stewart-Jones, who were my research assistants. They were absolutely instrumental through the whole process, especially Jen, who was with me nearly every trip. The First Nation of Nacho and Acknowledgements, their help was essential. They're great to work with, great guys up there. And I really appreciate their help. Transport Canada and Permafrost Net provided guidance throughout the process. And Yukon Highways helped a lot with licensing and allowed me to do this experiment, which saved a lot of work and made things much easier for me. And that's all I've got.
Okay.
Awesome. Thank you very much, Hugues. That was very interesting. It's really highlights the importance of snow on the thermal regime of permafrost. So do we have any questions from any of the attendees? Again, you can raise your hand, type it in the Q&A, or pop it in the chat. I can't see if there's any.
I could ask a question while we're waiting for more.
Sure, that'd be great.
I never worked in this, so yeah, first, thanks for this nice presentation. It's really interesting, and we are sometimes thinking about as well, like the influence of snow on our permafrost temperatures. So I was wondering, because I've never worked in this region, like how is the precipitation pattern there? Is it like a lot of, like a little bit of snowfall the entire time, or is it more characterized by like very intense but rather sheltered snowfall? Because I make it when you compact the snow layer.
Yeah, it's really important for my project, especially. Chris would have more of an idea about what the general conditions are in the area, but I found that it was fairly consistent throughout the freezing season, the snowfall, and the depth for my experiment peaked later on through the winter, and it seemed to increase fairly steadily. But yeah, Chris would have more of an idea of what general conditions are like.
I would say that the in central Yukon, there is usually quite a lot of snow in the first 2 months, so October and November, and then it tails off a bit. But one of the issues that is associated with climate change is the increase in snowfall, particularly in the second half of the winter. Again, in this area, because there are very few big bushes, there's a lot of redistribution by snow. And so the accumulation at the side of the road is early in the winter because it's an obstruction. And there are many willows at the side of the road, bushes that have grown at the side of the road, because the side of the road, being a little bit like a ditch, is a wet and moist environment, and the bushes grow very nicely there. And when the road was constructed, there was enough gravel placed down, gravel and other materials placed down, that immediately close to the road, the moss has disappeared, right next to the road. But so there's a small area, maybe 2 meters, over which the willows can grow very quickly. And that means that those will accumulate anything when the snow is blowing. And so blowing snow is really, I think, the greatest source of snow, and that will come off the tundra without much difficulty. There's a big source of snow. I don't know if those comments are at all close to what to answering your question.
Yes, thank you.
So we have a question in the chat from Lorene, and she's asking or saying that she's interested in doing some similar snow compaction. Have you ever had to deal with getting permission to use snowmobiles in an area where snowmobiles are prohibited?
Well, the short answer is I've never had trouble because I've never tried it. And alongside a highway, the highways department has a right of way, and in this case, it's 30 meters from the center line. So it's a 60 meter area in which they can do whatever they want. They don't need permission. They just can go in and do whatever they want because it's justified in terms of the safety of the road and the safety of the integrity of the highway. There are places where, particularly now, the snow machines have very big paddles on the bottom of their track. And this is for people who want to go and do snow machining in very steep gradients and this sort of stuff. And there are people who are getting annoyed about that because where the snow is not deep, then these snow machines can wreck the tundra, wreck the surface vegetation. That in the Yukon, at least, there are places where they will have rules about when it is allowed to go on the tundra. So the way they get around this is to say the snow must be 6 inches deep or 15 centimeters or 30 centimeters, or they have some value that they use. And when that has been measured by the conservation officers at different places, and they've said, yes, no, we've got enough snow now you can go. And the prohibition is before then. This does not help with understanding permafrost because it's that time when the snow is very thin that is critical for the freeze back. So for that, I would suggest that you use skis.
Interesting. So I have one of my own questions. What kind of maintenance is done along the road? Like, is there any removal of vegetation growing along the embankments? Like you said, willows grow, which would obviously trap snow. Is part of regular maintenance removing those to prevent snow from accumulating along the side of the embankment?
Yes, there is regular maintenance to remove willows, but it's a strange contract because they're not allowed to remove willows in the early part of the summer because of nesting birds. So it's one of those contracts where you don't know if the work is actually going to take place because the people who are doing the work can only go there once the birds have, the fledglings have left the nest. So it's never quite clear when they're going to start to do this. But there is a very clear intention to have very little vegetation close to the road and certainly a gap of about 15 meters. And the reason for this is that they don't want wildlife, not just the birds, but little wildlife sitting in the bushes and then all of a sudden coming into the road in front of a vehicle. And a caribou is not a big animal. It's about the same size as a person. So 6 feet. So a caribou can come through the bushes. And if the bushes are sufficient, you won't see the caribou. And then all of a sudden you smack the caribou with your vehicle. So the result is that the bush cutters, that stuff takes place in a more haphazard way than you would imagine in a country like, for example, Switzerland, where they would say it will start on this date and it will end on that date. That's the end of it. In Canada is much more flexible about how people are going to do things.
Oh, interesting. I never would have thought that would be a reason why willows weren't cut, but I guess that makes sense. Do we have any other questions in the chat? I have a few more that I can continue with, or we can call it a day. Maybe I'll go one more, kind of a philosophical question rather than a science one, but I think it's still important. Is like, in all of your years of doing field experiments and being out on the land, what have been some of the biggest barriers to doing your field work, and what are some of the ways that you've overcome them?
I would say that the biggest barrier is often you don't know who is going to be your assistant until they materialize. So as with many things, whenever I've spoken to a person who runs a business, I've asked them what is their biggest problem, and they say personnel problems. Managing people is far more difficult than managing the environment or managing your skidoo. If your skidoo is broken, you can fix it. If you need more food, you can buy it in the store. Those sorts of things are easy to do. The weather is fine. You just wait for a couple of days and it'll be okay. We've been stuck in Ilisarvik cabin for 36 hours with a howling blizzard outside. That's fine. We can just wait. We have lots of food. We have a stove that keeps warm. We're good. But if you have a grumpy person, or if you have a person who doesn't show up, right? Or if you don't know, if somebody all of a sudden something happens and they can't come and you were relying on them, then it's very awkward. And what used to be the case is that people would always bring somebody with them to be their field assistant. So then what happens is that you come from the south, you make an arrangement, you bring the person, and that's an arrangement where you're agreeing about, you will take this flight, and there's a lot of preparatory work that gets done, so the person comes. But if you are working with other agencies who are in the north, then you don't actually know what's going to happen until you get there. So you need to be flexible enough and have enough friends and contacts that you can be able to deal with whatever happens. But I would say that's the biggest challenge, is not knowing until you get there about what's going to happen. But it doesn't mean that it doesn't mean that these problems are insurmountable. They can always be fixed. Always. We always find a solution. But it's just a problem that you can't think, you know the problem in advance, and you cross your fingers and you get there, and maybe it's completely fine, but maybe it isn't. For example, in Pat's case, we were assured for 6 months that a contract would be in place for people to compact the snow. And this was going to be done by a bulldozer, and it was going to be arranged by a northern agency. Well, 2 weeks, was it 2 weeks before Pat went to the field, they said, "No, we can't do it."
This is after
So then I'm thinking,
Whitehorse, by the way.
Sorry?
I just want to mention this is after I'd already moved to Whitehorse.
Oh, he's already in White. That's right. He's already in Whitehorse, and they said, "No, we can't do it." So then I'm stuck. I've got 2 people, Pat and Jen, in Whitehorse. We've spent lots of money getting them there. We've got them for the whole summer. They've had to rent an apartment, a house, and all of that is set up. So all the front end money has been done. And then the partner says, "Oh, no, we can't do it. Sorry about that." So then you say, "Well, and then we're just astonishingly lucky, because the First Nation of Jardin, they said, "Don't worry, Chris, we'll look after it." Just like that. I told them the situation, we'll look after it. So it's the business of having enough friends that when you're in trouble, somebody's going to look after you. And you're going to look after them a lot of the time as well, in other ways. But it's those sorts of relationships which really make a huge difference to the operation of a field program.
Huh. Well, that's definitely something that's true. I think we've probably all experienced something like that during field work, but it's good to hear that doesn't just happen to me.
Oh, no, it happens to everybody, but it's just that you have to be ready and you have to think about how to solve the problem.
Yeah,
and it's just something that needs to be done. But I would say that is the greatest single challenge. I don't think if some people would say, "Well, we don't have enough money to work in the north," well, then what you need to do is to tailor your activity to the resources that you have. So that's a challenge. But you have to do that. Some people might say, "Well, that it's too cold in the winter and the weather conditions are bad." Well, then you just means you need more time, because you have to work. You have to wait to the time when it's going to be good weather and you can do your work. The logistics are a big problem, but again, that means just thinking in advance and making sure everything gets to the place when you need it to be there. COVID has been a big issue. It's delayed lots and lots of things. And there are some people whose field programs have just vanished because of COVID. But again, in our case, we figured out what is the minimum data that we really need to collect, and then find people who can do that. So there are ways of working around these things, but the most important thing is, never to say, oh, this is too much, I'm going to quit. There was something that our son used to watch where there was this thing, never give up, never give up, never let them get you down, right? Don't externalize the problem just and think that you're a victim. Think that you can be part of the solution, and then you'll get there.
Yes, I totally agree. Well, it looks like there's been no other questions that have come up from the audience, and it's 1:21, so I'm guessing we don't have enough time for the next presentation. But I think I say this for all of the attendees. Thank you very much to you, Pat and Dr. Byrne. It was really great to hear about some of the practical sides of permafrost science and how we can learn a lot of important things from field experiments. So with that, I hope to see everyone again next week for our final lecture by Dr.